Alright, so as I mentioned, let's restart from where we were last time. Can anyone please remind me what we talked about last time? We introduced a new concept. Say again. We introduced the concept of non-homogeneous equations, which is like the mathematical side of our problem. Why did we introduce the non-homogeneous equation? Okay, so why did we answer? Does anyone have the answer to these questions? Anyone know why we introduced the non-homogeneous equation, differential equation? This is because we moved from free systems to forced systems. So when we talk about forced systems, it means that we have an external force that is applied on our structure. Is a force that is that of course must be a function of time, the force that changes in time. And when we introduce this new force to the system, and I'm going to share the screen so we can also look at the So when we introduce an external force to our system and we look at the free body diagram, we write the equilibrium equation. From the equilibrium equation we plug all the forces. Before we had only the force of the spring for a system like this. Now we also have the force, the external force, again it is a function of time, equal to mx double dot. When we rearrange this equation, what we obtain is something that looks like this, which means that now we have this term as well. We used to have mx double dot plus kx equal to 0, but now we have mx double dot plus kx equal to f of t. And this is not homogeneous anymore. This is not an homogeneous equation, it is a non-homogeneous equation. That's why we introduced the concept of non-homogeneous equation. Also, of course, this equation can be written in a standard form when we basically normalize with respect to the mass that is in the system, so that we have our term k over m, which is the square of the natural frequency, and then we have this uppercase f0 divided by m, which is the normalized amplitude of the external force. So now that we have this standard form, we can solve the equation, the differential equation. When we solve the differential equation, the total solution is given by the summation of two contributions. One is the solution of the corresponding homogeneous equation, and then we also have to add another contribution, which is the solution of the particular equation, which is, the particular solution of the equation, which here is indicated as x sub p of t. This is a general form. We have one unknown, which is this amplitude x. How do we find the amplitude x? We can simply apply we can find the first derivative, the second derivative, we can plug them in our equation. Once we plug them in our equation, we can simplify, and then we can obtain the amplitude of the particular solution as a function of the parameters of the system, which means as a function of the external force, the k and m, and also the frequency of the external force. Once we find the particular solution, we also need to find the total solution, which means that the solution of the homogeneous solution has the same form that we saw before. We add what we just found, and then in the same way at this point we apply the boundary conditions, which means we apply the initial position and initial velocity. For the initial position we can simply call it x0, which means we take the position, we plug 0 here, here and here, and then we obtain an expression for a2, in this case one of the two constants here, a2, and then similarly we can derive the first time. Once we derive the first time, we introduce again our initial velocity. We can call it v0. When we plug 0 here, here, and here, we can significantly simplify this expression, and then we obtain an expression for the other constant, which is a1. We found a2 in the other page, we found a1 here. We can just plug these two, and then we have the total solution of the non-homogeneous differential equation. Please keep in mind that this solution here is valid only when the external force is F0 cosine of omega t. If we change this even slightly, the solution will be different. Make sense? Any question about this? Yes, so the question is about the source, the origin of the non-homogeneous term. So from a physical point of view, the non-homogeneous comes because we have the external force that again shows up here and then eventually here. When we solve the equation, the solution of a non-homogeneous equation is given by these two. So we have the contribution h hom, which is the solution of the homogeneous, and then x part, which is the solution of the particular solution. So this one here, well, I call this total, which would be the solution of the non-homogeneous, like this one here. So the total solution, or the solution of the non-homogeneous, will be the solution of the homogeneous and the particular solution, summation of these two contributions. Make sense? Alright, so again, now that we ended up here with this, then we looked at a problem. We had this system here with an external force. The external force has the same form of the force that we saw before, so we already know that the solution will be in the same form. Also, we had 0 initial position and initial velocity, so with 0 x0 and 0 v0 we can simplify significantly. We were asked to find the mass of the object, and then we can do a little mathematical trick, basically, to convert, let's say, this difference between these two cosine functions in the product between two sine functions. So if we have this product between these two sine functions, we can simply say that the maximum amplitude occurs when this is equal to 1. So it means we are looking at this contribution only. And then when we plug all the numbers, we can obtain the mass to be 0.405. Make sense? Any question about what we saw last time? Alright, if there are no questions, we can move to the next case, which is a little bit more interesting actually. So now we are going to analyze a specific case, which is the case where the natural frequency of the system. So to find the natural frequency of the system, we look only at the elastic constant of the spring and the mass of the object. So we compare this quantity with the frequency of the external force. So we said that these two quantities are independent from each other, because again the natural frequency depends only on the system, the frequency of the external force depends only on the external force, of course. So there could be a situation in which these two values are very similar to each other or even equal to each other. So we are going to analyze basically the case where omega is equal to omega n. So again, this omega would be the frequency of the external force, and this omega n would be the natural frequency of the system. Now, if this is the case, and we look back at the solution for the particular the particular solution that we found before, we said, okay, the solution of the particular solution would have this form here, and then we ended up with this form of the particular solution. Now, in a case in which omega n is equal to omega, it means that omega n squared is also equal to omega squared, so it means that this difference will be equal to 0. If this difference is equal to 0, it means that this quantity basically goes to infinite, which mathematically is acceptable, but physically, from our point of view, is not. So it means that if we are in a situation in which omega n is equal to omega, we have to use basically a different solution, a different particular solution. And again, this is something that is done as a trial and error, pretty much. So again, in this case, when omega n is equal to omega, the solution, the particular solution that we can use has the following form. So we have xp of t equal to t times the amplitude x times sine of omega t. Now we have this form of the particular solution, but similarly to what we had before, we still need to find this amplitude x, because as of right now this is just a constant. So we have to find the value of this constant based on the different parameters of the system. So how can we do that? Similar to what we did before, we can calculate the second derivative, and then once we have the function and the second derivative of the function, we can plug these two in our equation of motion and see what happens. So in order to find the second derivative, we have to find the first derivative first. So this is a product between two functions, so we have this first function and this second function, where x of course is a constant. So the first derivative will be x times sine of omega t. So this is the product of the derivative of this times this, and then we have to add this function multiplied by the derivative of this one. So we have t and then big X. The derivative of sine of omega t would be cosine of omega t multiplied by omega. We can slightly simplify this one. We can put x in common. So we have x times sine of omega t plus omega t cosine of omega t again. Now we have to find the second derivative. So for the second derivative we can consider this as a constant, so this remains like outside, and then we have the derivative of this quantity here, which is omega cosine of omega t, and then derivative of this quantity here, of this function here. So we have omega cosine of omega t, derivative of this one times this one, plus, omega t sine of omega t. I'm going on the other line because there is no space, times omega, and then the derivative of cosine is negative sign, so there will be like a negative sign. So this negative omega multiplies this one. So even in this case we can slightly simplify. So we have this equal to x 2 omega cosine of omega t minus omega square t sine of omega t. So we did the summation of these two terms, they are the same, so that's why we have the 2 here. And then the negative sign goes here, omega and omega become omega squared, and then t sine of omega t. So now that we have the function and the second derivative of the function, we can actually plug these two in our original equation. So when we plug, what we obtain is the following, is x times 2 omega cosine of omega t minus big X omega squared t sine of omega t plus also another big X omega n square t, again sine of omega t, and this will be equal to the term that is on the right hand side, which is f0 cosine of omega t. Does it make sense? So can we simplify this a little bit more? Yes. So here, since omega square, since omega and omega n are the same, remember that we are under that assumption that omega is equal to omega n, these two terms, one is positive, the other one is negative, are actually equal to each other, because if omega is equal to omega n, we can simply get rid of these two. So basically at this point we are left with the particular solution so we can simplify, so sorry, another step. So we have 2x omega and then cosine of omega t still there equal, so we got rid of this one and this one, so we're still left with this term here, f0 cosine of omega t. Even in this case we can simplify more, because we have cosine of omega t on both sides, so we can get rid of this one, get rid of this one, and then now we are left with 2x omega equal to f0, which means that our term x, which is exactly what we are searching for, will be equal to f0 divided by 2 omega. Now that we found this one, that x, the big X is equal to f0 divided by 2 omega, we just need to take this one, we can plug here, and then we find the particular solution. So we have that the particular solution is equal to t f0 divided by 2 omega multiplied by sine of omega t. Makes sense? So now we found the solution, now we found the particular solution of the non-homogeneous equation. Remember that the total solution is still given, this is like as a reminder that the total solution is equal to the summation of the solution of the homogeneous equation and the particular solution. So basically now we found this portion of the solution. Exactly like we did before, we need to add the solution of the homogeneous equation and the particular solution, which means that our total, like x of t, will be equal to a1 sine of omega t plus a2 cosine of omega t plus this term here, which is t f0 divided by 2 omega sine of omega t. Yes. You're talking about this term here. So here we have we plugged basically the expression of the second derivative, which is this one, x times 2 omega times cosine of omega t minus x omega squared t sine of omega t. This is the solution. If you remember, the equation is x double dot plus omega n square x equal to f0 cosine of omega t. So if you know, here this omega n square is multiplied by your particular solution, which is what we had here, tx sine of omega t, tx sine of omega t. And then equal to f0 cosine of omega t. So basically we plugged here. In the standard form of the equation. Other questions? So now that we have this one, what should we do? Are we done? Can we plot our function? Can we plot our response? Or we are still missing something? Very good. Now we are not done yet, because we have to use the initial conditions, initial position, initial velocity, to find these two constants here, a1 and a2. So which means that we have to do the exact same thing that we did before. So we went through the initial condition in terms of initial position. So we have that x when t is equal to 0. In this case, we call this initial position x0. This becomes very simple, because when we plug 0 here, we have 0 here, 0 here, and 0 here. Sine of 0 is 0, so basically these two terms go away. Cosine of 0 is actually equal to 1, so we are left with a2 only. So it means from this condition we obtain that a2 is equal to x0. We can calculate the first derivative of our solution, which is x dot. So we have a1 omega cosine of omega t plus a2 omega sine of omega t that multiplies -1, and then we have to add the third term, which is f0 divided by 2 omega, and then this is multiplied by sine of omega t plus t omega cosine of omega t. So this is obtained by deriving our solution here. A1 sine omega t plus a2 cosine omega t plus f0 over 2 omega sine omega t. So when we derive, we obtain this one. Now we can use the initial condition in terms of velocity. So when we plug the x dot at t equal to 0 equal to v0, again this simplifies significantly, all the signs go, so this goes away, this goes away, this becomes 1, this becomes 1. So basically what we obtain is that a1 omega is equal to v0, which means that a1 is equal to v0 divided by omega, which means that eventually we have that x of t, so this is the total solution, is equal to v0 divided by omega, that multiplies sine of omega t, and then the second term is x0 cosine of omega t, and then we also have our third term, t f0 over 2 omega sine omega t. Any question? Okay, now we come to the most interesting and most important part actually of this discussion, because now we can actually plot this function here, assuming that we know a certain value of initial velocity, a certain value of initial position, assuming that we know what kind of force we have as a external force, and then of course so what we obtain here is when we plot, we obtain something that looks like this. So the amplitude, the amplitude of displacement in this case actually increases with time. So now I think it's a little bit more clear why we always need to look at the natural frequency of a certain structure, and what we want is always avoid that the frequency of the external force is the same or very close to the frequency, to the natural frequency of the system. Because when we have a certain structure and we excite the structure with a force that changes in time with a certain frequency, and that frequency is again very similar or the same of the natural frequency, the response looks like this, and this phenomenon is called resonance. So again, very important in structural analysis that we make sure that every time we design a certain structure, the natural frequency is very far away to whatever external force like that changes in time is applied as a different again a different frequency with respect to the natural frequency of the system. Makes sense? That's a very good question, and we will talk about this in a little bit, but eventually, in a couple of lectures, I think, we will look at the response, like the amplitude of response. Instead of looking at it as a function of time, we will look at it as a function of frequency. So we will have a certain like plot where we have like normalized quantities, where here we have again a certain function of the external force, and then here we will have a certain value of amplitude. Again, these quantities will be normalized. If you look at the amplitude of displacement when the frequency of the exciting force changes, the response looks like this, typically. So in this case here, this value would be the same value of the natural frequency of the system, where you see a significant increase. Now we are looking at discrete systems that are like 1 degree of freedom, so theoretically this response would go to infinite before and after. So if you want to look at the mathematical analysis only, basically it will look like this. Again, because this is under the assumption that there is no damping, and also we have a discrete system with just 1 degree of freedom. In reality, again, when we talk about damping, we will see that this is the actual response. So every time we get closer to the frequency, to the natural frequency of the system, it is always a dangerous situation, because we can have a sudden increase of the amplitude of oscillation, and of course if we have too much displacement, we can have too much deformation, which means we can have like plastic deformation and eventually rupture of the whole structure. So when we design our structure, we always want to be very far away of the natural frequency of the structure. Make sense? Yes. Well, in that case you would find like an equivalent stiffness of the system and an equivalent mass of your structure. Again, we are analyzing now a structure that is made out of one single mass and one single spring. Of course, this is just an idealized situation, an ideal situation, but in reality you will have, assuming that you have discrete systems, you will have multiple springs. So you can have multiple masses in, again, multiple degree of freedom systems. So this is for discrete systems, but then for continuous systems, like can be a beam, then you would find an equivalent. It could be like a composite, for example, because actually concrete is a composite material. So in that case you would find an equivalent stiffness and an equivalent mass, and then from those, if you want to estimate the natural frequency, this is how you would do. So again, very important concept, resonance. Again, we always want to stay away from the natural frequency of the structure. I would like now to, so right now we can keep this, again, keep this in mind, because from maybe later or even next time we will look at it more in detail when we introduce the concept of damping for force systems. So I would like now to take a little step back and go for a problem.